Is there fumata blanca or not?
I don't know. Not yet. For avoiding the people.
Exactly. It's a risk prevention.
Really?
Yes. We were forced to put this.
What is this?
There is a
Like this.
it's a hardware limit.
If you really want to, you have to take it out first.
Exactly, but it takes some time. So maybe.
Okay, recording is already active, so
We should not say too
I
many.
think everything set up, right?
Okay. Yeah.
No sé si acabamos ganando.
¿Qué tal? Alessandro, no, una pregunta sobre eso que has mandado del paper ese. Sí. No usan datos de JPAG, las normas. Vale, vale. Digo, te pregunto porque no me voy a contar los normas, quiero saber. Sí, sí, claro.
Que efectivamente tenían que ir a
Pero entonces pues eso no cualquier
si haces algo relacionado con JPAG, incluso si estás usando los ciclos de JPAG, ya parece que es vale.
Usarlos. No, sí, está bien. Yo no tengo curiosidad.
Son solo los datos, está bien
O sea, y eso lo tienes miembro.
las semillas.
Si no eres miembro,
What can you move yourself
No, this is
No, bueno, estaba diciendo que es como.
I think this is something that you have to do here.
That's okay.
Juan, can you hear us?
No, it's okay.
¿Qué pasa?
Quiere quitar todo.
No, it's fine. It doesn't.
If not, it's...
I think the European Union will not be happy.
De luego de cerca.
No, it's okay. It's okay.
No es cierto.
That is the
Jesús,
Dime,
eso
Juan.
lo puedes quitar dándole a en la tablet opciones de visualización o algo así.
Vale, un segundo.
Si quieres, hazme videollamada y te voy diciendo.
Títulos, ya reacciones, selección de grupo. A ver, seguridad, vista, en vista.
Vista, opciones de diseño.
Vale. Normal,
Vista.
apagado.
Sí, en opciones de diseño apagado o desactivado o algo así.
No.
¿Correcto?
¿No? ¿It's okay?
Yeah,
Perfecto.
Muy bien.
Okay. So Juan, it's okay, we start?
Whenever you want.
I think so. Okay, so let's start. Thank you very much for being here. For me, it's a pleasure having here today to Professor Peletier. Most of you know him. He's a well-known astronomer in many topics, but in particular in stellar populations of galaxies. To me, it's a pleasure because it's been a colleague of me for many years, and he participated in my thesis, so it's a part of a very good friend. Okay, so he made an effort to stop by Cefka. He's been for 6 months in La Palma, more or less, and now he's driving back to Netherlands when he's originally from, and he's living now. And he came to Cefka to visit us, to visit Cosmology and Galactic Archeology, and I would like to thank Renier for making this effort. So Renier he's from Groningen. He did his PhD there. Then he moved to the CFA and also to ESO. Then he became a support astronomer in La Palma, the ING. And then he got a permanent position in Durham University, then Nottingham University, and finally he came back to Groningen, where he is now working. And he also, during some time, he was the director of the astronomy department in Groningen. So it's a pleasure that Renier is here, and he's going to talk us today about the DREAM, a new stream finder. So thank you, Renier.
Well, thank you very much, Javier. It's been a pleasure here. Also yesterday, where I saw the Savalama Observatory, where all the developments that are being taking place here in Teruel, and especially this Galactica, which is a really example for an outreach place. And I'm trying to get some ideas about to implement in Groningen or north of Groningen, where we have our exhibition center for the Dark Sky Park, and what to do, because I mean, you always need to improve, so you always need new ideas how to contact, how to tell the public about astronomy and about why you're doing what you're doing here. So I'm very pleased that you have this good contact here with the town and with the local government and so on. So what I'm going to talk about is a development that we started, was started in a collaboration with computer scientists in about 8 years ago. So it was started when we got the Sundial EU network with at that moment 14 students. Nowadays they only have 10. And these students, and this was a network to which contained astronomers and computer scientists. And what do you do to make them work together? So you try to develop methods which are applicable to topics in astronomy. So and then one of these, the most successful one is Streamfinder OneDream. And you can see, as I will show, it took a lot of effort to make sure that it did work and that it's useful to use. It's all open access. You'll see it in a minute, and you can use it as well. You can download and see whether you can make it work. Afterwards, I will talk a little bit about dwarf galaxies and maybe some possible applications with JPass. Just because I'm here and you might know a bit more about that. So this is LAT. This is a paper by Alfonso Aguerri et al. And our collaboration. So where we try an ant crawling method. These are ants, hormigas in Spanish. And they crawl, they go to where food is, but they also put some pheromone where they walk. And this is also food. And so other ants follow them, and this way you get an increase of density. So it follows where there is high density, the density becomes higher. And so you let this run, you put your image, you fill with ants, depending on some initial conditions, but usually you have some point cloud or whatever. And you let the ant crawl for a while, and so basically enhance the density in certain regions. And that method, so this is being shown mathematically how this works. And it's actually, it's a machine learning tool, so don't expect too much from the mathematics and don't expect too much, just a method that works. That's mostly what it is. I mean, you can do experiments and see how it works and what it cannot do and what it can do, and that's probably the best way to test it. So, for example, here you test, so you have a number of structures, and these structures we put in noise, in big noise. And the output is then basically the same, so you can completely get this back from the noise. And that is what showed that it works. So this is a structure of cosmic web, we run it through LAT, and you get this structure. So it finds linear structures in here. So it enhances the density, it finds the high density areas. And so we found that this method is very good for finding filaments in astronomical data. So a lot of this has been described in the thesis of Petra Arot, who has been invited recently, I can say this, last week, for the final round of Women in AI. So he's really a very successful person. And she's in this thesis, there are several examples and it's also worked out how it needs to be run and see. So when you have computer scientists, they produce usually codes, and the codes might work, and for them they're fine. But that's it. And then you need an astronomer who works this out and who is interested in applications, in computer science programs, can follow them, can make them better, and can apply them. And that is this person. And you need both. You cannot have only one, because then in the end you have something which is fairly useless. You probably talk about it. So this is the first paper. This is the second chapter of the thesis. which is where this method is being tested, being applied, how to use them, and so on. And so there it basically consists of 5 different programs. One is the LAAT, then gets rid of the noise in the outer parts and produces the structure. EM3A is a second tool, and EM3A moves the points, so finds the maximum and moves the points closer to the center. So it tries to then, so it does another density enhancement. Then in every place, and this is a cosmic web or whatever it is, then every point it finds a dimensionality index. And this is here 3, and here it's 1, because it's a linear feature, it's a cubical feature, it's a cluster. And then there's a crawling. Crawling then takes this data in the one-dimensional side, connects bits by bits, and it makes makes a fit of the features. So it gives you it gives you say a linear curve for all these things. So that which you then basically use. And SGTM produces a probabilistic distribution of this whole final result. So which you can use. All of this is available, as you can see on the toolbox on this website. It's still a bit of an experimental website. The website is being made by Rory Smith, who is at the moment in Chile, but he has been part of this collaboration for quite a while. So these are the 5 tools, 5 programs that are being used, which I mentioned. On this website, you can find also a number of applications that I've mentioned, but you can also find some other applications. And you can find the software, software is in C++ and Python. And then first there were a lot of things in we call it MATLAB, but it's always been rewritten into Python. So now we're here in this paper. This is the third chapter of all of them have been published now. Is basically looking at and applying it to astronomical data and seeing how well it works. And so this is first you try to see whether we can find the filaments and characterize them well. But how do you define a filament? This is not very easy. I mean, you don't really know how to define it. How do you know whether a filament is correct? So this is part of the cosmic web, and here you get some results that come from LAAT. This is being so that you can basically look here. This is what LAAT gives. This is what a competition. So there is lots of filament finders around, but very few are publicly available. Very few there's a software available. Disperse is one of the ones that are mostly used. Use here Disperse, and so you take the area, and Disperse finds basically this, and LAAT finds this here. But what is correct? Well, we don't know. I mean, you don't know whether it has to have more wiggles or not. So they did lots of experiments, and so here you have a bit of the area. Disperse gives a much more wiggly result than LAAT, just because the polynomials that's being exposed through here is required to be as low as the order as possible. And so here there's an experiment. We take only 80% of the data, remove 20% of the points, then remove 40% of the points, and see how stable the result is. And you see that in the case of LAAT, the result is still very stable. It almost doesn't change. And in the case of Disperse, well, things do change a bit and so on. As a result, we claim that LAAT produces results which are as good as Disperse and probably easier to use. So this is, and since Disperse was used basically as a standard tool in cosmology by many people, then this can also pass the test and can be used by many people in for this kind of applications. There's a paper by Liebeskind et al. 2020 or so, where they compared 10 different methods, finding filaments and so on in the cosmic web. And we've also now compared our results with the result there, and they compare well. So that's the comparison with disperse. And this is a comparison with some cosmological simulations. Now, the second thing we can do, this is cosmological. So, okay, let's go to do some real data. Here, what we do here on this paper, this is with Maria Angela Rausch, who is going to get married actually in India in a month's time. But she was my postdoc, and so what we do here is we try to determine where what the life scale structure in the local universe is like. This is a major problem because you need to know the three-dimensional distances and positions of the galaxies around us. And determining distance of galaxies is not easy. You can get redshift, but redshift, especially in the local universe, has lots of so-called fingers of God. So it determines being dependent on the neighborhood on galaxies being nearby and so on. So then other methods are used, like the Fisher or fundamental plane or those kind of things. And so there are catalogs of nearby galaxies and their distances. And the only thing is not there, which for me, because I like dwarf galaxies, there are not many dwarf galaxies, so massive galaxies that have been used. Otherwise, the rest of them are not good enough to produce the data that are needed for fundamental plane and so on, like velocity dispersions and so on. So here's the catalog by Temple et al., which has lots of objects in there, and then taken the region of the Fornax Iridanus supercluster and try to. So basically, this is the region of that, and they try to then use that to see where is the cluster itself, is there something else, and so this is basically the Fornax Iridanus supercluster. The method then gives lots of different connected sub structures, lines, and this is what comes out. And so you see there a number of these of clusters, and the next one you will see is a bit better. So Fornax is this is Fornax with Fornax A, and then there's some more objects around. This is the Iridanus, there's Dorado somewhere. But anyway, you get this some structure, and it's difficult also because it's a three-dimensional structure that you have to pretend in 2 dimensions. Anyway, this is what we get, and this is probably the best that is available. On the other hand, we need much more data to do it well. We need, for example, distances of dwarf galaxies determined using, say, surface boundary fluctuations or other ways. So, but with new surveys like Euclid, for example, more things can be done. Okay, so this is cosmic web. And this is more or less, you can't go that much farther because at some point, well, you get redshifts and then you can determine structures there. We could do in principle analyze a simulation. This is what Roger Smith is mainly doing. But what you really like is you like to use observations. But the observations are actually not that good nowadays to do this. So this is our small number of small areas. This is the paper. And then you can do science. So the science, so once you have this, you have then the spine. Then you want to then look at you want to look for how do galaxies form. And of course we know that objects in a cluster form fast, form early on, and maybe in a cluster there's only early types, ellipticals and so on. And in the field, outside clusters, there's a lot of galaxies still forming stars. Now, what happens in these filaments? Is there some behavior? Are galaxies on the spine older or more elliptic, more early type than galaxies away from the spine. So this kind of work that is just starting. And so here you see a structure that we look at, for example, we have defined the spine, and then we look at the fraction of early types as a function of distance to the spine. And you see that it's clearly ellipticals is disappearing. So this plot is actually this is not a very good plot because the total is 100%. So it's not that everywhere it has to be 100%, but you see clearly that early types are going down and the late types are going up. And we are at the moment busy with dwarf galaxies. We use the sample of dwarfs found using machine learning from the DEF survey by Tanablidis et al. And trying to see how they evolve as a function of distance from the spine. And you clearly see that there are effects. So now we go to Gaia. Gaia, of course, for this method is, which works based on points clouds, Gaia is actually really ideal. Right? There's lots of points you can study. The problem in the disk of Gaia is that there's too many points. So at the moment, the method cannot handle it. And when you get to numbers that are bigger than 10 million or so, it cannot do it. But let's say here we use an algorithm that selects only low metallicity stars based on the Gaia data, based on the I think a velocity position cut by people in our department, by actually and so we look in the halo and we try to find streams in the halo. So how do you do that in Gaia? So Gaia has, we have this color magnitude diagram. Problem with Gaia, of course, is that there are way too many stars that are interloping. So these are foreground stars here. This is noise, this is all kinds of things. And your selection sits, so you put in an input as an input saying, well, I want to go for something close to the Groningen cluster or something that's around -2 because the halo is like this, so you go for it. Here, which is in this case, we put the -1.7 isocone here, and you make artificially some kind of cut around it. So you at least you remove this stuff and you remove this stuff, and you always try to find what you see. Then, of course, with Gaia, then you also have proper motion. Proper motion is actually better than parallax, because parallax, if you go farther than a few kiloparsecs from the sun, doesn't work very well. So you use proper motion. And so what you do here is you look at position in the sky. So this is the selection you make. You then run LAT, because LAT then finds and enhances stuff. And you find this structure. For this position of the sky, find 152, some place. And you see, well, it looks to be like some stream-like feature here. And you look then in proper motion. And here you see clearly that there's 2 clumps in proper motion. Do they have anything to do with this? But you can make it better. So you can then say, well, okay, let's refine things. Let's refine the, so this is here. So now let's go and refine the stars that you choose. So you go closer to the isochrone. And then of course you get less background, and you can get more structures here, around here. You see it also then it becomes easier to see in the proper motion diagrams, and you get even closer, and then you see this. Okay, this was the Jellum stream. This had been found. This is, of course, here it's done better because it was large, you can isolate more. But this has been, the stream had been there. But now what we can do here, new, with proper motion, we can say, well, let's use multi-Gaussian decomposition here. And say, this is one clump and the other clump. and can we then try to see what belongs to what? And so this is Gaussian mixture modeling, and you say that this is it. So then you can basically, for every star, determine with a certain probability to which stream it belongs. This one, that one. And actually, what then happens is, this is one component, broad component, and this is a narrow component. And that's actually quite interesting because maybe that has some astrophysical meaning. And so, okay, then we started working with the S5 team, and that's a team that's using, I think, the Australia AET, has determined lots of radial velocities of stars, and especially of low metallicity stars. So they had substars in this area for which they had radial velocities. Gaia problem is Gaia, you don't have radial velocities. So you have the sixth dimension, and so we could then isolate the stars, these stars, which have radial velocity within this stream, and the rest of them we then have to assume that they're probably not part of the stream. And so this is then what you get. And you still see that you have the narrow component and the broad component. But spectra also give you a composition and a velocity. So spectra also give you a metallicity and a radial velocity. And so if you look at the narrow component, you see that the radial velocities are also narrow. The radial velocity minus the radial velocity of a fit, of the average. And in terms of metallicity, well, there it doesn't work very well, but the metallicities from these stars are probably not good enough. The errors on the metallicity are quite large, so this doesn't work too well. And so what do you get? A broad component with a velocity dispersion in here of about 20 kilometers per second, and a narrow component with a velocity dispersion of 4 kilometers per second. And what does that remind me of? Well, working with dwarfs, this is a dwarf of mass about 10 to the 7 or 10 to the 7 solar 10 to the 7 solar stellar mass. And this would be a globular cluster. So if you have a globular cluster falling in a dwarf, falling it, and one globular cluster for such a dwarf is quite fine because you expect them to have about one. And this falls in, then you see the globular cluster and the galaxy falling into the stream. So, and that is made, the result is strong because of LAAT that was run in the beginning. So, to conclude so we have some more applications. If you look for a lot, you can find some more papers, and there's more applications of streams around the globular clusters, where you can use then the metallicity of the globular cluster to do some initial searches. And the aim is, of course, that we continue doing more of this work. But I'm not going to talk about this now. What we can conclude from this is it's a robust method, it's fairly fast. We are trying to make it such that it's going to be faster, it can do more objects, more points and so on. It works in principle in an arbitrary number of dimensions. So you could use it, you could start thinking, well, now I'm not going to use the space of x, y, z or so. You can use space x, y, metallicity, J-pass band 29, and so on. So it can be very flexible. You can start thinking about how to apply this. It's good at denoising, and it produces for making the filament produces excellent results unless we then disperse and a probabilistic model of the distribution of points. So now, this is where my new student Marco Canossa comes in. We started then thinking, well, we like to use it to find streams, filaments around galaxies. Pity that David Martinez is not here, but I mean, I like to come to his meeting in October to talk about this. So then, of course, this is an image. So you have to then convert an image into a point cloud. This is possible. There's lots of ways of how to do it. But the problem is, of course, is that you don't have too many points, but it's for small amounts of data, it seems it's working at this moment. But there's a couple of things that are being improved. So now there's a dynamic radius. So first, LAAT is only for, at this moment, LAAT is only looking for, so the ants can only crawl with a step size of say 1. But if, for example, there's a gap between the two, then the ants can never go to here. So you automatically have, you stick to the gaps stay. But if you have a variable radius, and that's the new LAAT, it's made by Felipe Contreras, who is a student of the Universidad Federico. No, it's a university in Santiago. I don't know if someone knows the name, but it's the university where Rory Smith is. But he was 2 years in Groningen where he did this work and so on. And this does produce better results because depending on the density of points, the radius can be changed. Next thing which we have done is if the density contrast is too high, so if you have, for example, density of 10,000 to 1 or so, then you lose all your points that sit all in the center. There's no point. So what you then do is we have now replaced the center areas where the density is high by some analytic potential, and then connected this to the points in the outer parts. And so that seems to work also. This Simone Velardi is doing this. He's a student of a new EU network, Educado, where also Marco Canossa is part of. Marco Canossa is working on detecting streams. So it's maybe interesting also for people doing Arrakis. So you like to detect things like this and things like this stream and so on. We are struggling with all kind of issues, but getting there. I mean, removing. If you have points in front, all the points has to be removed or be modeled or things like that. And you have to have the galaxy itself, which the galaxy itself should not affect the points themselves. So we're working on this, and he is doing his PhD on this, and it's trying to do so. I mean, maybe you have heard about the work of Juan Miro in Madrid, who did by eye found lots of streams around objects, but here we want to make it automatic. And doing this automatic is, of course, will save a lot of time, but I mean, making it automatic is actually very well. It takes a lot of stuff to do this. We're also thinking about Alma data cubes, so just H1 data cubes. They are 3-dimensional, but the point is sometimes you don't know whether a cloud belongs to some neighboring clouds or it does. But that's one way you can denoise things and then fit, for example, rotation curves or some kind of models to it. And so, we're using it also now for simulations. More ideas, more will follow in the future, I'm sure. So, I mean, what time is it? 3:03. So, if possible, I'd like to talk a lot about 10 minutes about dwarf galaxies, what we've done, and how this could be used for JPass or with JPass. So, this is Star Formation histories of Earth-type galaxies, but particularly dwarf galaxies. So, this is the idea that this is a very old idea already, well, very old, not very old, 20 years, that massive galaxies formed all their stars at the beginning, and this could be at redshift 5 years later. And the fainter the galaxy gets, the longer the time. It starts also a bit later, but then the longer the time takes that the stars are being formed. Yes? And I mean, whether this was an idea, whether this is correct and so on, this wasn't really. This is what people thought. Of course, what happens here is very difficult to determine. So this was just on the control of Daniel Thomas who did this. But now we can do better with more data, better data, and so on. So for dwarf galaxies, so for massive galaxies, this is more or less what stays. But for dwarf galaxies, just the data were so bad at that time we couldn't say much. nowadays we know a lot about local group. And in this work, we talk about the Fornax cluster. Where you can go to 20 megaparsecs, which is a bit farther than the local group, quite a bit farther, and where you can use techniques used for unresolved stellar populations. So this is the situation for the local group. This comes from Star Formation Histories, basically determined from color magnitude diagrams, where you can see how wide is the red giant branch and where the stars sit, and there's these. And people then determine, so you can see that the stars, there's a lot of, say if you go to the most massive star galaxies, they're like here, and they have formed stars all the time, right all the time. These are fainter galaxies, and you mostly see that the stars are formed early on and in a shorter time scale. But there's a lot of variety from galaxy to galaxy. Now, in our work, we did this with the SAMI instrument that has 12 IFUs at the same time, and with a bundle of 15 arc seconds. The bundle is great here because you just can add up all the light. They're not talking about anything gradients or whatever, but just add up all the light. A high spectral resolution, for dwarfs you need high spectral resolution, otherwise you cannot measure the velocity dispersion, for example. You can do the Star Formation history, in fact, but yeah. Very deep integration, and so that's where you can go to about 10 to the 7 stellar mass. This was done with bundles. This SAMI on the AET had all these things in a bundle of 1 degree. So we all the time had to select objects within 1 degree from each other. And so that's why you then get an object together, and there's some, and there's some. But it's a representative sample in general. So, what do we get? First of all, you look, so why is this interesting? First of all, you look for the alpha over Fe. So people, alpha or magnesium over Fe. This is something that, why do people study that? Well, because this is available, and this, you notice this from galaxies. This is one of the magnesium, and people generalize it to alpha, which on the other hand might not be completely true nowadays, is something that seems to be varying in from place to place. So in the halo is high, in the disk is low. And it's the result, what people think is that if the enrichment comes from massive stars, which produces these are massive stars that produce a lot of, they produce in supernova type 2, and they throw this whole nucleus, which is very strong, into the interstellar medium. They produce a lot of oxygen, neon, magnesium, and so on, and relatively little iron. If you have other types, if the evolution goes slower, and you get a lot of supernova explosions from combination of white dwarfs with red giants and so on, it takes longer. So that means that the star in the center can produce, can go further and produce iron, and then a lot of the stuff is what comes out is iron. Well, so you have these two things: oxygen or magnesium, which oxygen is difficult to measure. So you have magnesium and iron, and when this varies, basically the oxygen, the fraction of supernova type 2 or supernova type 1a varies. And I call this just speed of star formation. It doesn't do with amount of star formation, but speed of star formation. This is fast, this is slow. And so this you can measure very well. Now, let's see what happens in dwarfs and galaxies in general. So this is the standard metallicity versus stellar mass or velocity dispersion. You find, I can use either this one. This one doesn't really matter because it correlates quite well. So you see for massive galaxies, this is the Atlas 3D survey, reanalyzed, so it has the same, it doesn't have any differences in method. So you see that when you go to lower mass, the metallicity in general goes down, and in the dwarfs, it tends to fall. There's some variety, but you have the age metallicity, degeneracy, and so on, which makes it hard to measure. Anyway. And the same with in this figure. Open is field and closed is cluster. Not important. But you see this is the general relation, but then when you go to alpha, things are interesting. So when you go to alpha, you expect, like metallicity, that it starts becoming same relation. No, you start seeing that alpha over Fe for dwarfs, the fainter you get, becomes higher. So what does that mean? That the speed of star formation is faster in dwarfs. You get this U shape. This is that's what you find. And the U shape is, well, you can show this again. This is trying to understand the metallicity relation. I don't want to show this too much, but then I go to the alpha here. So what you get, this is including now the local group. Local group, dwarfs from Fornax. This is a coma sample. This is outer 3D. So you get this U shape for the formation of that. Do we understand that? Why? Well, out here in very faint galaxies, you form everything at once, like in the halo. And then it's so small, the galaxy, it cannot keep. So, for example, this is a dwarf near the Milky Way. It's often close to it. All the gas is expelled, and then that's it. So this is why alpha is fast. You don't have the time to make it. You don't have the time to wait to make the alpha higher, lower again. And if you then put here some star forming dwarfs, which we also had, they are here. The star forming dwarfs have magnesium iron alpha around 0, which is like disk of 100 away, which is slope star formation. And that's correct. The star forming dwarfs have slope star formation. So basically, we're detecting here how the stars in object form. So this you can do basically in every galaxy. And so, this idea of this star formation is something that can be tested. And it can be tested quite well. And maybe with JPass you can measure the magnesium line or the alpha. Let's say it that way. So, I mean, we did some details here. This is for all the elements. We took some spectra for the brightest ones because for the fainter ones it's difficult to look at the atomic number versus solar abundance. And seeing, and this is work from Pomeroy, and you see some elements are higher and some are, and in the dwarf it's opposite basically. So now let's go to the star formation histories again. We go back to this picture. And now to see what happens to the dwarfs. Well, the data are as good as we can get at the moment. There is no 8 meter that can do dwarfs. Bit of velocity dispersion smaller than 20, but you should try. So you get all kind of mixes, like in the normal group, and you find basically that what you do find is that the star formation histories as a function of loopback time. So here we put the object. This is the Atlas 3D curves. So this is a very massive galaxy, forms all the stars at the beginning. Less massive, less massive, less massive. And then you get, okay, less massive, then this one is more or less the same as that. So you get here, you go here, and still, so the dwarfs follow, these dwarfs follow the relation. And you see it here in the other way. Now let's add the local group to it. And so here you get local group, and here you start seeing that this the lowest figure goes back up. So you have this U shape again, up and back. So this is then the star formation history of galaxies all the way from massive to very low massive mass. And here in the figure you can present this. So this is a fraction of stars of a certain age as a for a certain mass. And so this goes like this, and it goes back like that. And this is the position where you have the longest range, the biggest range of ages of stars. Around 10 to the 7 so on. So this is why these objects are maybe still very interesting to study, because they're not as boring as these ones, where all the stars get formed in the beginning. And these ones are also rather boring because you get one burst of star formation. And now the question is, what can dwarf do here with these objects? So, I mean, you have long integration times, yeah? And in principle, there's 50 bands or 56 bands or whatever, and you have different environments, cluster field and so on. So spectra can be recreated. So can this kind of features, the star formation histories, can samples be made, and maybe stacking whatever, to test these theories, to see what happens in the field? Because everything I did was for the cluster. I don't know, this might be something. And that's the end. Thank you very much. Yeah.
Questions?
Yeah.
Thank you, Renier. Very, very nice talk. This is a little bit of a technical comment. You said that the lab was trained as a machine learning algorithm. Can you comment a little bit on the training strategy, how it was?
There's no training here. This is well, why is it machine learning? I don't know why people call it machine learning. It's not the same as using neural networks. Yeah. But here it is by what you do is you train the ants, or you let the ants just move and move and move and move and move, and after a while they are done. They don't get any better. And yeah, I mean, this is what people also classify this as a machine learning tool. So there is no, that maybe say there's no right answer here, because if you run the ants with a different definition, you get something a little bit different.
So how do they know where the ants should go?
They don't know, but the ants go. They try to go where food is, so they try to go where density is.
So they get a reward when they go
to higher density areas. Yes, and also areas where other ants have been, because then they make the density a bit higher.
Okay.
So
yeah. So in the filament finding code, so you just use the position of each galaxy. No weighting based on like the light or the size of the galaxy. Nothing. Just,
yeah. Weighting. So basically, once you need to convert intensity to points, number of points.
Yes.
And so we experiment in this moment. At the moment, we have done what we've done is just linear, but linear is not. We could also do it logarithmically. I think logarithm might be very good, but then logarithmic has issues with zeros and so on. So this is something we're going to work on to see whether, because I mean, here it's for detection, right? So you just need to find area. You don't care about how much there is, because later you can go back to real data and measure it.
Yeah, it's mainly for like something like the clusters, like the BCG is usually huge, and then many of the smaller cluster elements are inside it. So you take them as separate sources, not just as one, in the algorithm to find the filaments, for example.
Yeah, I mean, of course, this is a complicated situation because it's very bright and there's a lot of background, so it doesn't really work very well. Because it all
it's
gets
mostly for the outer.
It gets all pulled towards the center. So what you can do is you can indeed represent some parts by potential, and then so I haven't done these ones yet.
Very nice work.
It's a comment. I think one of the additional capabilities that GPAS is going to provide is the fact that because we are observing everything, we are going to have a very large statistics. We also can make slides in Redshift. I mean, probably because of the depth, we won't go to Redshift 1 to observe dwarf galaxies. But I think we can make some discrimination between, local dwarfs and probably some different slides of Redshift to a certain limit. Okay? The point here is that I think that in that case, this U-shape that you saw before, I would expect that the most massive galaxies, when you go to high redshift, the alpha Pi are going to increase. and they're going to reach the level of dwarf galaxies, because essentially dwarf galaxies, they only had a, let's say, one star formation episode, and that's it. Whilst massive galaxies have even if they form their stars very early, but they are then contaminated by other mergers, other minor galaxies that have ended up being modifying the MGO.
Yeah.
So I would expect that a high redshift, both dwarf and very massive galaxies will have the same or similar amount of MG over Fi. In your plot, with local galaxies, actually dwarf galaxies have even more extreme MG over Fi. Okay, so if we are able to see this plot at different redshift beams, we may see an evolution of this view.
Yeah, but I guess for this telescope will not make it because it's just.
Maybe a few.
You need to convince someone to build a 10 meter with 50 filters. Yeah,
We should talk to the.
no, I mean, so yeah, but I think one of the things for high redshift for dwarf, the only thing is globular clusters. They tell you something about the beginning. And so because the globular clusters basically are remnant from that area in which, so for the stars, yeah, for the massive galaxy, yes, you can do. I think this was all way too much towards ellipticals. I think going to spirals will change things somewhat, not too much, I guess, but that might make the interpretation a bit more interesting.
Yeah, I'm very curious to see, you said that this, the LAT algorithm could be applied to images, but you didn't show any results. Do some tests?
I'm still fighting with my student on this, and we are. So we have run the whole cavity sample already, but it's not. I don't like it very much. So we need. The problem is all these neighboring stars and galaxies, and it's complicated. So it will be there, and in half a year time should be a lot better. Yes. So.
Questions? Comments? Okay, if not, let's thank Renny again.
Yeah, that's right. Yeah, it was maybe a bit too quick.
It's very nice and many applications can use this planet.
Voy a parar la grabación, ¿no?
Sí, Juan, ya puedes parar.
Vale,
¿Salgo
perfecto.
también de aquí?
Muchas gracias, Jesús, y perdón por el lío con los cables.
No pasa nada, no te preocupes, Juan. Pasadlo bien por ahí, que apago aquí el poli, ¿no?
Sí, tú simplemente lo desconectas, no tienes que apagar nada.
No, salgo de la
Desconecta el
reunión y ya
HDMI,
está, ¿no?
el HDMI de. Desconecta el HDMI del ordenador y lo otro lo dejas. Y apaga el proyector.
Pero me salgo de la reunión, ¿no?
No tienes que. Bueno, la reunión la voy a cerrar yo, o sea que no te preocupes.
Vale.